This video is a follow-up video of the Mailman problem part 1 and 2, so if you didn't have the opportunity to watch the part 1 or the part 2, you can click to watch the part 2 on the link above. In this video, we are going to calculate the expected value of the length of a path among all the possible paths that the Mailman can take. So now let's address the final question, which is the expected value of the length of a path. So we are going to note this expected value big E, and what we know is that there are n-1 factorial possible paths. So n-1 factorial multiplied by the expected value E is equal to the sum for all possible paths m of the length of this path m, which can be written as the sum for all possible paths m of the sum from e equal 1 to n of mi minus mi minus 1, which is equal to the sum for all possible paths of m1 minus m0 plus the sum for all possible paths of mn minus mn minus 1 plus the sum for all possible paths of the sum from I equal 2 to n minus 1 of mi minus mi minus 1. So as you can see here, we are breaking down this sum in three different sums, and this is going to help us because we know that the value of m0 is equal to 1, the value of mn is equal to 1, so this is going to help us identifying individually each number for each sum. So notice that for that sum, the number m1 can take n-1 different value, same for the number n-1, and when we have chosen among this n-1 value, there are still n-2 factorial possible way to arrange the number m2 to mn-1. So we can write that this is equal to n-2 factorial of the sum from x is equal to 2 to n of x minus 1 plus n-2 factorial of the sum from x equal to 2n of x minus 1. So basically these two sums are the same, so this is why we are writing the same sum, and we will take care of this sum a bit later. So this is equal to n-2 factorial multiplied by 2 because we are basically having the exact same sum here. Sum from x equal to n of x minus 1. And this can be written as 2 multiplied by n-2 factorial of the sum from x prime equal 1 to n-1 of x prime. And this is equal to 2 n-2 factorial. So as we have seen, this sum is well known and is equal to n multiplied by n-1 divided by 2. So we can write that this is equal to, we can take off the 2 here, n-2 factorial multiplied by n-1 multiplied by n, so we basically have n factorial here. So now let's go back to that sum over here. So we are going to note the value mi as x, mi minus 1 as y, and if we choose a value for mi and we choose a value for m minus 1, there are still n minus 3 mi that we didn't choose yet a value for, so there are n minus 3 factorial way to arrange this number. So we can write that this sum is equal to n minus 3 factorial sum for x that should be different from y, but both between 2 and n of the absolute value of x minus y. And of course, I should not forget to mention that this choice has to be made for each I between 2 and n minus 1. So we have this that will repeat from I equal 2 to n minus 1. But because this quantity no longer depends on I, we can write that this total quantity is equal to, if we sum this from 2 to n minus 1, we are basically repeating everything n minus 2 times. So this is equal to n minus 2, n minus 3 factorial to the sum for x different from y, both of them between 2 and n, of the distance between x and y. Notice also that by symmetry, there are as many ways to select x that is lower than a y than to select x that is greater than a y. So this sum is equal to 2 times the sum where we consider that x is strictly lower than y. So this is equal to n minus 2, n minus 3 factorial sum for x strictly lower than y and both of them between 2 and n of y minus x that we know is strictly positive. Note also that it doesn't really matter if we assume that sometime x is equal to y, because in that case we are summing 0, so whether we write that x must be strictly lower than y or lower or equal to y, it doesn't really change the sum, so we can put a lower or equal here. And so we can write that this sum is equal to n minus 2, n minus 3 factorial of the sum. So this time we're going to make a change of variable, and this change of variable is the change x equal t plus 1. So this is the sum for t that is greater or equal than 1, strictly greater than y, lower or equal than n, of y minus t minus 1. And now the trick that we're going to use is to reinterpret this number as a sum of the number 1. So this is equal to n minus 2, n minus 3 factorial sum from t that is greater or equal to 1, strictly lower than y, lower or equal than n, of the sum from u equal 1 to y minus t minus 1 of the number 1. So here basically we are summing the number 1 y minus t minus 1 time. So this is exactly equal to y minus t minus 1. And now we do the change of variable v is equal to t plus u. And we can write that this is equal to the sum 1 t y n of the sum from v equal to t plus 1 to y minus 1 of the number 1. So here, note that we are summing a number v in such a way that v is strictly greater than t because it's greater or equal to t plus 1. And this is also strictly lower than y because it is lower or equal to y minus 1. So we can rewrite this sum as n minus 2, n minus 3 factorial, sum for t that is greater or equal to 1, and v that is strictly greater than t, but also strictly lower than y, and y that is lower or equal to n of 1. And now, thanks to this trick, we see that this sum is basically summing all the possible ways that we can select three number t, v, y in a specific order such that t is strictly lower than v, that is strictly lower than y. And we select this three number among n possible number. So this number of ways to arrange three distinct numbers in a specific order is well known, and this is equal to n choose 3. So finally, we can say that n minus 1 factorial multiplied by the expectancy is equal to n factorial plus n minus 2, n minus 3 factorial multiplied by n choose 3, which is equal to n factorial plus n minus 2, n minus 3 factorial, n multiplied by n minus 1 multiplied by n minus 2 divided by 3 multiplied by 2. So this is basically a developed version of n choose 3. So we have this that is equal to n factorial plus n minus 2, n minus 3 factorial multiplied by n minus 2 multiplied by n minus 1 and multiplied by n. Everything divided by 3 multiplied by 2. And of course, I forgot the number 2 that should be here, because as I was explaining before, there are as many ways to arrange x strictly lower than y as there is way to arrange x strictly greater than y. So the number 2 needed to be here, here, and there. And we need to put it here as well, here. So we can cancel out the 2 here, and we have n factorial plus, so here we have n minus 3 factorial multiplied by n minus 2 n minus 1 n, which is equal to n factorial. So n factorial plus n factorial multiplied by n minus 2 divided by 3, which is equal to n factorial multiplied by 1 plus n minus 2 divided by 3, which is equal to n factorial multiplied by n plus 1 divided by 3. So at the end, we have e that is equal to n factorial multiplied by n plus 1 divided by 3 divided by n minus 1 factorial, which is equal to n multiplied by n plus 1 divided by 3. So at the end, the expected value of the length of the path is equal to n multiplied by n plus 1 divided by 3. Thank you for watching this video. This was a more complicated problem that we have seen in the past. And of course, there are many ways that we could have solved this problem. And if you know about another, maybe more simple way to solve this problem, please feel free to let me know in the comments.